Hello again, everyone. Now that we've gone over two ranking algorithms, cosine similarity and BM25, let's talk about how we can score our document collection efficiently with this cool data structure that we made, our inverted index. All right, now you've already seen that you can do a Boolean and quickly, but how do we do these ranking algorithms that sort of seem like they should be scoring all documents and everything, and they're going to produce scores? Anyway, so again, we know, and I've alluded to this multiple times, we will not actually compute a score literally for every single document. Documents that contain none of the query terms will never be returned. All right, so with that in mind, let's recall the following. So recall that all of our ranking algorithms, at least that we are studying, are of the form, or when we get to language modeling, can be made to be in this form, of a score for a query in a document that is a summation all over the, all over the, basically the keywords or the queries that form the intersection of the query and the document. All right. And then we have some sort of weighting for the keyword in the query multiplied by a weighting for the keyword in the document. This is written a little bit differently than I put it on the board before, but it's nice to be comfortable with seeing things in different ways. So again, we're always going to end up with something that's basically, we're going to sum things up over our set of our keywords, our query terms, whatever we want to call them. So there are two main approaches for scoring with indexes. The first is, I'm going to actually, we're going to say the first one is term at a time. And the reason I'm going to say this one's first is because it's easier. All right. And then there's doc at a time, document at a time. Both of these are illustrated in the course textbook, so you can refer to that. I'm going to actually use an example that mirrors what's in the course textbook, so that should be able to, if you don't follow what's going on here, check out the course textbook, and of course, if that doesn't work, go ahead and ask me questions via CampusWire. So we've got this general form. We have these two approaches that I'm going to go over with you. Now, I don't want to be here and try to be calculating BM25 by hand. I could do it, or doing the cosine similarity by hand. I want to have an example that's really easy. And so what we're going to do is, for illustration purposes, we wouldn't actually have a ranking algorithm like this, but if you wanted to try it, you could. So only for illustration purposes, we're going to give ourselves a simple scoring function, which basically says, let's count the number of times query terms appear in the document. All right. So we'll take the term frequency of the term in the document. So we'll go over the set of the unique words that are found in both the query and in the document. So notice what is their intersection, basically. So over those terms, we'll just sum up how many times they appear. So this is the total number of occurrences. This is not a great methodology, okay? That's why we have those other things, in particular BM25, which is very careful. If this worked well, we wouldn't have spent, there wouldn't have been so much effort to come up with BM25 or all the new modern techniques. So this is very crude. And as you'll note, it is missing the whole IDF component, which was a major discovery. All right, so that's going to be easy. We just have to count how many times the words appear in the document. All right, so let's take this example from the book. And yeah. So their example from the book is, so this is an example from book. And it's an example with the idea of a very small collection. But the query they have is salt, water, tropical. We have no idea what the user is looking for, doesn't matter. But what we want to do is we want to compute the scores. All right, so with term at a time, what we do is as follows. All right, so term at a time, let's just put this up. We basically have an algorithm that is for each query terms postings or list. So this is, we're going to go fetch for this term its postings list from the inverted index. We're going to compute partial scores for each document in the list, and we're going to store these partial scores in what we'll call an accumulator, which is basically just a hash table. All right, and then once we've done that, so this is what it means by term at a time. Going through each of the query terms first. Oh, we'll take the first query term, fetch the postings list, compute partial scores, record them for all the documents in that postings list, then go back to the next query term and repeat and repeat. Now we've gone through all the query terms in all the query terms. Then we'll go and we'll sort our accumulator by score and report the top scoring documents. All right. It's not going to be that hard. So let's go back. I told you we're going to have this query. So yeah, go through all query terms, maintain partial scores, then sort and output. All right. All right, so let's look at this. So for term at a time, start with the first query term, all right, which is salt. And so we have our inverted index, and we fetch for salt its postings. And we find that its postings tell us that document 1 has salt appear in it once. And so this first one is the doc ID, and the second one is the count. Is our notation. Okay. we are going to maintain our accumulator. Over here. It's going to be a very simple hash table again. So we can put in a key and go ahead and increment the value or set it initially. Now this postings list, and I'm going to, actually I should write this a little lower. It also has document ID 4 with a count of 1. So what we do is, and I'm spacing this out so it'll all look nice at the end. Anyways, so we start processing this list and we go, all right, document 1 has a count of 1. And remember our scoring function here is this really trivial thing, which is the count of the term in the document, the term frequency. So we go to the accumulator and we go, hey, have you seen document 1? And it's like, no, I haven't. Okay, so we're going to put in 1, document 1, and it goes, at the moment, its score is 1. All right, and we go down our postings list, and there's no other documents. We're not iterating through documents. We're going down through the postings list. Oh, document 4, yep, it's not there, so we'll go ahead and record it with 1. Great. Now we're now done with that query term. Now it's time for the next query term. Let's fetch water from our inverted index. All right, so water, document 1 also has it once, but then document 2 has water once, and document 4 has it once as well. All right, so we're gonna go down this postings list now. Document 1, oh yeah, I've got this key there. Okay, well, add the count to that and store it. All right, so this then gets changed to 2. Oh, document 2, oh, nope, haven't never seen it before. So document 2 gets stored its count of 1. Document 4, yep, I've seen it. Oh, add 1 to 1, so this becomes 2. All right, next, tropical. Tropical has document 1 containing the word twice. Document 2 contains tropical twice, and document 3 contains the word once. Okay, so wonderful. So now we just go down our postings list. Document 1, yep, I've seen it. Oh, I need to add 2 to 2, so this becomes a 4. Take document 2, yep, add 2 to it, that becomes a 3. Document 3, never seen it before, so we're going to add in that count there. All right, so now we've processed all of our query terms. We've done it a term at a time, storing partial scores into the accumulator. Okay. You couldn't do this for BM25 just as well, just a little bit more complex calculations. Same for cosine similarity. BM25 is nice and clean and easy. Anyways, and so again, because it's just a summation over the terms, and so you can do the exact same thing. Now that we've concluded that top loop, now we're going to go and take this, and we need to sort it by our score. You might, in your programming language, have an easy way to do this. Some languages would not. And so you may very well take this, copy it to an array of, score and doc ID, and then sort by the score, and then output, okay? Of course, you'll have to look up, the doc ID to the doc no and things like that, but you're old hands at that now. And so our final ranking after we sort it is as follows. We've got a ranking which is a doc ID and a score. And so our best score happens to be document 1, and it has a score of 4. The next best is 2 with a score of 3, and then 4 with a score of 2, and 3 with a score of 1. And we've produced a ranked set of results, okay? And we scored all of the documents that had these terms. Maybe there were actually 10 documents in the collection, 1,000,000, who knows? But only these documents contained the terms salt, water, and tropical. And we've done a term at a time ranking. And you can see that it's actually really has the ability to be really fast and successful. The downside, is there a downside to term at a time ranking? Well, the downside is that there basically can be lots of memory needed for the accumulator. But it has a good side, that it has less disk seeking compared to doc at a time. All right. Why less disk seeking? Well, this is about as low disk seeking as possible. Again, with the idea that your inverted index is actually on your hard drive, for you, you're bringing your whole index into RAM, making things easy, so it's not quite the same way. But if you had to go to the hard drive and read just the postings list for each of these, you'd seek for salt and do a sequential read on the hard drive. Then you'd seek for water and do a sequential read, and tropical and do a sequential read. That's great. What we're going to see with doc at a time is that we're going to be using all the posting lists at the same time. So there's potential for us to have to be constantly seeking between the postings lists as we go down. All right. But the opposite advantage is going to be it doesn't need as much memory. So it trades these things off. All right, so let's look at doc at a time now. Okay. So now we have our example on the board. You can actually look at it this way. What we do is as follows. I'm going to show it, and then I'll write down the notes about it this time. The idea is we fetch all the posting lists, all right? Or we start to fetch them, okay? But we take all the query terms, and we need all the posting lists. And then what we do is we process and compute the complete score for a document and store it, okay? Then we move on to the next document and store it, and so forth and so on. All right, so first we look at this posting list and we see, document 1. All right, and so we look at the other posting lists and we say, oh yeah, what we're going to do always in these matters is we're going to keep track of where we are in them. Okay. So we're currently here, we're currently here, and we're currently here. And it just so happens that each of these at the start of their list happens to be document 1, so that works out just fine. And so we just go down through them all and we sum this up. 1 plus 1 plus 2 is a score of 4 for document 1. Great. Now we go for each of those. We go and advance basically what we would think of as our pointer, but basically our index of where we are in the postings list for that list. So 4, 2, and 2. And what we do then is we look across our posting lists where our current index is, and we say, who's got the smallest number? Which is, who's got the smallest doc ID, I mean. Oh, document 2, I see, is the smallest one out of all these. So we're going to now compute the score for document 2. All right, so 1 plus 2 is 3. Great. Now, since we just did these, we advance them. We don't advance that one. All right. And then, all right, we'll look up. 3 is the lowest one, so we're going to compute the score for 3. Only one of the lists is currently at 3, so its score is easy to sum up and is 1. This then is, its index is at the end. All right. We know it's at the end. We're done with this list. It will never be used again. Then, we look, yep, 4 is our smallest one, and it gets a score of 2. And these get advanced, and they're past the end. Now that all the posting lists have an index that's past the end, we know that we're done processing the posting lists, and we can take these scores then and report the ranking. And in fact, it's almost already in rank order here, but it'd be document 1 is 4, document 2 is 3, document 4 is 2, and document 3 is 1. Let's actually talk about some of the smaller details about this. Okay, and I'll write it out for you. So for doc at a time, this pen, done for. All right. So doc at a time is for each of the query terms, retrieve its inverted list. So these are the postings. Get rid of this pen too. And then using all the lists, we walk down the lists, totaling up current documents score. So we're always going to say, all right, who's got the, I'm looking at all these lists. I have the current index. Which one has the lowest ID? For that ID, I'm going to now look at the lists and sum up the score. Now, basically, I'm going to compute the entire score for that document. That's all the information I need. It's in the postings list. Yes, you are likely to also need to go look up some other things. What's that document's document length? You're going to need that for BM25. Of course, you will have pre-computed as well. What's the average document length in the collection and stored it somewhere? You're also going to have information about the number of times Word appears in the number of documents it appears in. You know that because you'll have the postings list, and the postings list length lets you know how many documents contain it. You also will have stored somewhere the total number of documents in the collection. So you'll be able to, through some storing of some information in advance and the postings list, compute an entire document score by looking across the posting lists that contain that for the query terms for that query. All right. Then 3, you're going to store the document's score in a priority queue of size num results. So if you need 1,000 results, you make your priority queues maximum size 1,000. You recall how a priority queue works is that you're going to say, yeah, I want you to keep these in, I want to be able to put these things in by their score. Please also store its document ID together, but you're going to prioritize them by score such that I can easily find out what is the minimum score in constant time. So you'll basically be, if the size is less than num results, just go ahead and add in the new document score. Once your priority queue is up to the size of the number of results that you want, you go and you quickly say, hey, in constant time, what's the minimum score that you have there? Is the current document you just computed a better score than the minimum score? If so, remove that minimum document and add the new one in there. And again, because it's a priority queue, most likely implemented as a heap, you'll always be able to do these operations. You'll be able to see what the minimum is in constant time, and you'll be able to remove and add in the new one in log n time, where n is only the size of the number of results. So these are very fast operations. And basically, you're going to keep track of what are the best num results documents after you're doing this. And the beautiful thing is, it's a priority queue. So when you're done, you just pull them out and they'll be in sorted order. Okay? Or we're going to repeat 2 and 3 until we've reached end of all postings. And then 5, output scores and the document IDs of the priority queue in sorted order. The priority queue makes this easy to do. One thing I want to mention, absolutely, doc at a time does not mean for document 1, compute its score, for document 2, compute its score, compute document 3, all the way through all the documents in the collection. Too many students make that mistake, okay? They think when it comes time to compute the scores, they are going to iterate through every single document in the collection. And even worse, they don't even use their inverted index. They'll do, they potentially will go through the entire inverted index searching for that document ID. You know, that's really bad. Then some students say, I'll make it a little better. Given a document ID, I'll go to the postings I need to go to, and I'll go down that postings list until I find it. And then I go to the next one and the next one, and I'll compute those scores. All right, great. Then doc 2, and they'll search the postings lists. That's not what doc at a time means. Those are gigantically inefficient approaches. So when students say to me, for some reason my retrieval is taking 7 hours, that's what they've done, all right? It does not mean that. Or even if they're like, it's taking a couple minutes. So after it's loaded, so after you load your index, you should like print out a message for yourself like, the index is now loaded. Now processing queries. And that should happen in a flash. You should be able to compute the scores for all the queries very quickly because it's all in memory and you're going to use these great inverted indexes and the proper algorithms. The homework always says, tell me what you used. Did you use doc at a time or term at a time? Invariably, when students say they did doc at a time, they didn't, because it's a more complex algorithm. And what they actually mean is, yes, I just simply, for every document in the collection, I went through and did a very inefficient approach to compute its score. Thus, the big piece of advice here is don't implement doc at a time. Implement term at a time. Term at a time just means fetch that postings list for that query, go down it, store partial scores in an accumulator, which is just a hash table. If you wanted to, you could even just store it in an array. We don't have that many documents, 120,000, 130,000, whatever. You just need an array of that size. And in those cell locations of the array, store the partial scores. It's easy. All right. Then, of course, then you would go through at the end and you'd find you'd have to, again, keep track of the doc IDs and sort them, but same difference. Anyways, term at a time, much easier. It's just a summation, and you're just creating scores for the documents in those postings list, and you just go down each posting list one at a time, sum them up, sort it all, output it. That's the way to go. So what about pros and cons of doc at a time? I think the thing here, pros and cons, is that the nice thing about it is that it's very memory efficient. All right. Because we're not, for a large collection, the number of documents that we might have to store partial scores for with term at a time could be really large. And then as we keep fetching and storing those scores, we end up hopping all around memory, which reduces our ability for cache performance and reduces the overall speed of things if we're trying to do things super fast. So the memory efficiency here can be really useful, but unless your posting lists are all in memory, this will result, so basically if it's on disk, in many disk seeks, because you're going to have to switch between those posting lists constantly, reading a bit of them from the disk, and they're in different parts of the disk, and so then you have seeks. Seeks are very expensive time-wise, and if you're doing concurrent query processing, you're potentially causing the disks to do lots and lots and lots and lots and lots of seeking, and you might end up with a very low overall performance for your server. Yeah, so as we'll do these seeks as we switch between lists on disk. And I have here my note, which is again the warning. It does not mean that you're looping over all documents in the collection. Okay, great. What do we do with really big collections? The web. Or even document collections that are too much for one machine to be able to quickly process. Big collections. Well, the basic idea is that there's multiple ways to do it, but a nice way is to distribute the documents across machines. So each machine gets a subset of the documents. They're disjoint, so we've just spread them all out over a bunch of machines. And all machines, so by machines, of course, I mean computers, all machines score, and then we merge the top ranked documents from each machine. All right. So again, this will result in, when comes time to do a query, that basically we ask all the machines that are involved in this collection to please compute their scores. So if we've divided the collection into across 10 machines, let's say, we should be able to compute those scores in 1/10 of the amount of time as if we had had them on one machine, assuming the same machine size and things along those lines. Approximately 10. So on those machines, it'll be 1/10 because it's 1/10 of the data. You know, they only have 1/10 of the overall collection. Each of them scores them. We receive those scores back with documents, and we just merge those sorted lists, and we've got our overall ranking. There are some complications to getting this done. One of the things being, I need to know things along the lines of the IDF. So I need to know how many times the word appears, how many times it appears in the collection. But I, as an individual machine, I've only seen 1/10 of the collection. So there are schemes to share the document statistics across the machines and so forth and so on, so that you can get this done. So it's not as trivial as it sounds, but it is one way to do it. The other way to do this, you could also distribute it by terms. All right. So, you know, you could distribute by terms. And so what I mean by this is a machine has a certain subset of the vocabulary on it. You've built an inverted index, and then you divide the inverted index across the machines. And so, saltwater tropical, it could very well be that salt is on one machine, water is on another machine, and tropical is on another machine. And then you just query each of those machines. It computes all the partial scores for salt, all the partial scores for water, all the partial scores for tropical on each separate machine, because the different terms are on different machines. And then we get that back, and then we do a final summation to combine all the scores for those documents, and then we rank them and we return them. The book explains that this is not commonly done. The distribution by documents is more frequently done. And you can read about in the textbook about some more of the pros and cons about doing that. But anyway, so this is how we score efficiently using our inverted indexes. Doc at a time, term at a time. Term at a time is easier, and that's what I recommend that you do on homework 4. All right, great.